In this video, we want to continue with our discussion of the precise definition of a limit. And I wanted to do one more proof here in this video, and then we'll be done with this section. So one of our limit laws is the sum rule, which says that if the limit as x approaches c of f of x is equal to L, and the limit as x approaches c of g of x is equal to m, then the limit as x approaches c of the sum of those functions is just the sum of those limits. And in this particular example, we want to go ahead and prove that using the precise definition of a limit. So how do we do that? As always with these, we start with the statement, let epsilon be greater than 0. What is that? That is some small positive value. We just assume it is a really small but positive value. That's what that statement means. We want to find a delta greater than 0 such that for all x within this interval, 0 is less than the absolute value of x minus c is less than delta. This implies that the absolute value of f of x plus g of x, so that's minus L plus m, is less than this really small but positive value epsilon. All right, so first by regrouping terms, we have, so we're going to regroup terms and we're going to rewrite this over here. So this f of x plus g of x minus L plus m is equal to the absolute value of f of x minus L plus g of x minus m. And it turns out that this is always equal or less than the absolute value of f of x minus L plus the absolute value of g of x minus m, right? That's using something called the triangle inequality, that the absolute value of the sum of two numbers is always less than or equal to the absolute value of, the sum of the absolute values. So, what does all of this mean? Let's look at what we're given. So this first statement up here is, since the limit as x approaches c of f of x is equal to L, then this implies then there exists some, and we're going to call it delta 1 is greater than 0, such that for all x in this interval, we have that the absolute value of f of x minus L is less than epsilon over 2. So up here, we're given that epsilon is a small but positive value. So if we look at epsilon over 2, that's still a small but positive value. And by our definition, since this limit exists, then any epsilon that we choose, including some epsilon divided by 2, these conditions must be satisfied. So there exists some delta 1 where this is true. Now, why do we choose epsilon over 2 here? That'll become obvious, or we can see that here in a few minutes, but that's not entirely clear at the moment. But if we change our epsilon to be epsilon over 2 that we're trying to satisfy this for, again, given our initial statement up here, we can find a delta that satisfies the problem when we choose epsilon over 2. So, well, similarly, there exists a delta sub 2, which is greater than 0, such that for all x in this interval, 0 is less than absolute value of x minus c is less than delta 2, implies that the absolute value of g of x minus ilm is also less than epsilon over 2. Okay. And now what do? We're going to pick delta equal to the minimum of delta 1, delta 2. What does that mean? That just means delta 1 and delta 2 are both small but positive values, or probably small, but certainly positive, right? So by these two statements here, delta 1 and delta 2 are positive values. Let's let this new delta that we're going to find just be the smaller one of those two. Okay. Then, if 0 is less than the absolute value of x minus c is less than delta, so again, this delta is just the smaller of those two values, we have two things. First off, the absolute value of x minus c less than delta 1. Implies, if this is less than delta 1, and which is equal or less than delta, so this interval is less than delta, so these x values are less than delta, contained within delta. And so, but specifically, since it is less than delta 1, we have that this is true just by what we're given above, right? If we have this interval, then for all x in this interval, we have this is true. Since delta is equal or bigger than delta 1, oops, I had that backwards. This is, I'm sorry. This is here. Since this range is less than delta, which is equal or less than delta 1, since we picked delta to be the minimum, then certainly all of these x values here are less than delta 1. And so by the above statement, we have this is true. And moreover, we have similarly, this is less than delta, which is also equal or less than delta 2. And so the absolute value of g of x minus ilm is less than epsilon over 2. Well, put all of that together. What do we want to show? Well, reminder that we want to show the limit here as x approaches c of f of x plus g of x is equal to L plus M. This means that we want this statement right here to be less than epsilon. We want to say that we've chosen some delta so that for all x within the interval x minus the absolute value of x minus c is less than delta, that this statement right here is less than epsilon. So let's see if we've successfully done that. So let's just start with our statement there, f of x plus g of x minus L plus M. Well, what is this equal to? Well, this is actually equal or less than absolute value of f of x minus L plus absolute value of g of x minus M, right? We already said this earlier by the triangle inequality, right? We said this one earlier. So this right here is equal or less than this. I'm just rewriting that. Well, this is strictly less than, right? F of x, the absolute value of f of x minus L is strictly less than epsilon over 2. So the absolute value of f of x minus L plus the absolute value of g of x minus M is strictly less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. So we have in fact got the statement that this here is strictly less than epsilon, which is what we wanted to show. And if we ever finish a proof, we either write QED or put a square there to show that we have completed our proof, or that is the end of our proof. And yeah, that completes the proof of the sum law on limits. We're not going to do any more in this class on this, but you can start to see what it takes to prove those limit laws, and you can get to see a little bit of how complicated that might feel at first, at least. But for this class, we want to assume our limit laws are true and assume a lot of these other theorems that we give in this class are true. But here you start to see how we might prove those theorems and those limit laws. But that's already been done, luckily for us, by people several hundred years ago. So we don't need to do that again. We'll just assume all of these theorems are true for this class. And that is where we'll end this video.